Hello again. Thanks for joining us. This is Space Nuts. I'm your host, Andrew Dunkley. It's always good to have your company, and I hope you're well. Coming up on today's program, we'll be looking at geysers on Enceladus. The James Webb Space Telescope has had another look at them after they've been previously seen elsewhere, and they've found out a bit more about them, and it's pretty amazing. Also, a star that may not be a normal star. This one could be a dark matter star, as a matter of fact. We'll get stuck into that. We'll follow up a couple of things that came up in the last program, just some questions that needed to be investigated further. And we will be looking at a white dwarf age issue, according to Rusty. We talked recently about Saturn's ring rain. David wants to bring that one up again, as well as his lunch. And Jeff is asking about what the view would be like from a black hole if we could possibly get inside one. Would be tunnel vision at the very least, I imagine. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me once again is his good self, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you?
I am quite well. Back to work this week. Back to normal. Back to business. Back to everything that I had forgotten how to do.
Yep.
After a month off.
Yep, that's what happens, isn't it? You come back and
does
it's
indeed
still there.
Yeah.
Well, maybe that's better than it all not being there at all.
Indeed, yes. It's good to have good people that can back us up. That always makes a big difference. So you come back and you go, well, that's a relief. Nothing's broken, nothing's missing, nothing's wrong. So it's always nice when you can rely on people, and that's what we've got. And yeah, plenty of things to talk about. So let's get stuck into it straight away. And this first story I find really exciting because there's a lot of attention being paid to Enceladus for all sorts of reasons, notwithstanding the potential for life. But these incredible geysers that have been recorded previously have been seen again, this time by the James Webb Space Telescope.
Yeah, so this is really quite exciting news. And it highlights, once again, the capabilities of the James Webb Telescope as a tool for science that's sort of par excellence. The observations have been made of Saturn's moon Enceladus. Now, we haven't yet seen those observations, so I haven't seen any images, and that's probably partly because the research paper that's describing this work is still pending, so it hasn't yet appeared in the scientific press, and I guess the people who are responsible for it are essentially, keeping their powder dry to basically stop the media getting hold of it before they've actually published it.
Yeah, that happens.
Which does happen, and you'd know that as a media person.
I've never done it myself. Gosh.
Well,
never break an embargo.
And I have to say I haven't either, because I get all these things that are embargoed, and I too don't break them just because it's the wrong thing to do. So, yes, I think that's what's happening there. But this is scientists at the Goddard Space Flight Center who have presented these results actually at a conference in the Space Telescope Science Institute, which is in Baltimore. It's a place I visited a long time ago. So going back to the matter in hand, Saturn's moon Enceladus, we've known since the flybys of the Cassini spacecraft in the early 2000s, I think it was as early as 2005, that the ice plumes being emitted from Enceladus' south pole were discovered then. In fact, what first hit the headlines, I don't know whether you remember this, because I'm sure you and I talked about it, but there were these things near the south pole of Enceladus, which were markings that were described as tiger stripes, because they do look a bit like tiger stripes. And then it was discovered that they were actually cracks through which what probably started off as water, but as soon as it hit the vacuum of space, became ice crystals, and that's what were being observed by the Cassini spacecraft. And in fact, Cassini made several passes through those ice crystals, so that using the equipment that it had on board, it could detect some of the chemicals that were in them, principally H2O, so water there, but also molecular hydrogen, and I think some silicates as well were detected, which tended to give you the insight that the water that was underneath the ice had been in contact with rock before it was spat out to form the ice crystals. And the molecular hydrogen was interpreted as being possibly symptomatic of the fact that there were these deep well, it'll come to me in a minute. The black smokers, that's the expression I was looking for, down on the floor of Enceladus's ocean, the sub-ice ocean, that there were basically hydrothermal vents in the ocean floor. So that was all very exciting. But of course, with Cassini's mission coming to an end in 2017, all that stopped. And so further research was not possible until now, when the James Webb Telescope has been directed at Enceladus. And they've kind of hit pay dirt, because they've discovered an ice plume that is far bigger than any of the ones that were observed by Enceladus. And that sort of makes you wonder why that might be. Is there one of the cracks, one of the tiger stripes has opened up a bit to allow more water through? Or is it something to do with the gravitational pull of Saturn? What's happening here? And so that's one of the things that is being studied at the moment. Apparently this ice plume extended quite a lot further than the diameter of Enceladus itself, which is 500 kilometers.
Yeah, that's one of the things they've discovered as a consequence of this observation, is how big these geysers are.
Yeah. And I remember from that time an image of Enceladus, which was taken when Enceladus was backlit, so the sun was behind Enceladus, but you could see that the plumes of stuff that were coming off Enceladus were actually feeding into Saturn's E-ring. The E-ring is one of the diffuse rings outside the main ring system. And that was great, because that answered the puzzle of where the E-ring came from. It actually comes from ice crystals that are generated by Enceladus. So all that's sort of backstory. But now we have these new observations, and in principle, we've got a new way of investigating these things, because the James Webb is equipped with some very sensitive infrared detectors, spectrometers, and things of that sort. It's possible that we might get some new insights into what chemical elements and perhaps even molecules are contained within those ice plumes. Although I think the bottom line really in the end is going to be sending a spacecraft to Enceladus.
Yes.
Going back to what we knew these jets contained, we've got quite a big list in addition to the ones that I mentioned earlier: methane, carbon dioxide, and ammonia. These are, of course, all organic molecules containing carbon.
And Babel fish.
Probably Babel fish as well, yes. If you need to translate from one language to another. Anyway, it might be even more exciting than Babel fish, if anything like that could be possible, because that methane could turn out to be from methanogenic organisms. We don't know that. But all of this still highlights Enceladus as a fantastic target for further exploration. And a couple of things come to mind there. A mission which is proposed called the Enceladus Orbilander, and that name tells you what it's going to do. It will orbit the moon if this goes ahead for about 6 months, and actually flying through those ice plumes, and then land and look at the exact details of the surface. It probably would not try and penetrate the the ice, though, that's the province of one that you and I have spoken about before.
Yes.
Something called eel, which is a bit like an eel, something called a snake robot. EEL is an acronym for Exobiology Extant Life Surveyor, or EELS actually. And one of the principal boffins behind that is Linda Spilker, who was with us a few years ago to give the Alison Levick lecture. The Linda Spilker being the Cassini mission scientist, so very, very well equipped to propose new missions. And I think EELS was one of the ones she was involved with.
Yeah, if that doesn't work, of course, the backup mission is the Black and Decker mission, which
yes, that's right. Or if you really need it, the JCB or the Caterpillar mission with the heavy lifting stuff. That's right.
Or the Ryobi mission. Yeah, any of those that can drill.
Yeah, that's right. Well, if you go with Ryobi, you only need one set of batteries and you can refill.
That's right. Yeah, I actually had I've got a Ryobi leaf blower, and the leaf blower died before the battery did.
Oh, that's interesting.
Yeah, it is, isn't it?
Yeah,
quite surprising.
Still very much alive, but being tall, I have to have a cardboard tube on the end to extend it down to blow away the leaves. Anyway, that's a different story altogether.
It is indeed. I must say, whoever thought of Enceladus Orbilander, I mean, gee, come on! Couldn't they come up with something better than that?
I think in the end it would have a nicer name. But yeah, like you, I'm finding this really exciting that the Webb Telescope now can turn its very substantial capabilities onto a moon like Enceladus. Certainly nowhere near the same resolution as we had from the Cassini mission, but lots to find out nevertheless.
Yes, and there's so much attention being paid to Enceladus and its similar cousin of Jupiter, which is, I'm stretching to remember the name of it. Hang on.
Think beginning with T. Yes, TI. No, Texas Instruments. No, TI is Titan.
I wasn't thinking of that. I was thinking of the other ice moon.
Titan's definitely an ice moon, but it's got a...
Yeah.
I mean, there are the other ice moons that we really know a lot about are Europa, Ganymede, and Callisto.
Europa.
Yes, around Jupiter.
Yes.
Saturn.
All prime candidates for potential life.
Exactly. Yeah.
What kind of life we don't know, but if we can get up there and find it and study it and see what it's made up of and whether or not it's the same stuff as us, that would be really interesting.
Exactly, because if we found life there, living organisms there, it would suggest that wherever you've got the raw materials for life and the right environment, you're going to get it. Interesting stuff.
And it would change the answer to the Drake equation.
That's correct. It would indeed.
Yes.
Yeah.
And that we're all hoping for that.
The Drake equation, though, it certainly puts one further input into the Drake equation, but it doesn't give you the answer, because that's all about intelligent life. It would be astonishing, though, if we found vertebrates or something with some kind of intelligence.
I keep saying it. Krill.
Krill, yeah, that's right. Hyper-intellectual krill.
I'm sure they're out there somewhere. All right. If you want to follow up this story, as Fred said, they haven't released the data yet, but I'm sure it will come to a website near you in the not too distant future.
Okay, we checked all 4 systems and skiing with a go.
Space Nuts.
Now, Fred, to another matter, that of dark matter. We get so many questions about this, so many questions about black holes. Anything that's got darkness involved is obviously of great interest in the astronomical world and to the layman too. But this is a really interesting story about a star system that they've known about for a while, but now a couple of astronomers or space scientists are saying, hang on a minute. This might not be what you think it is. This could be a dark matter star.
Indeed, that's right. So let's do the backstory. This comes about from observations made by Gaia, which is an astrometric spacecraft. So Gaia is basically something that measures with incredible accuracy the positions of stars in the sky. In other words, their right ascension and declination, the equivalent of latitude and longitude on Earth. This Gaia system is so accurate that it basically allows us not just to measure the positions of stars, but to measure their positions changing over time. And so you can basically look for the motion of stars. For example, if a star is orbiting something else, you will see that motion from the measurements made by Gaia. And that's what's happened here, in that a star which is nearly the same mass as the Sun, it is a Sunlike Star, so it's something like 93% of the mass of the Sun, but also has similar chemical properties to the Sun. So it's got similar what we call metallicities, the amount of material other than hydrogen that's in its atmosphere. And you can determine that from the spectrum of the star. But the Gaia measurements revealed that it's actually orbiting something else, which is invisible. And you can look at the analysis of the orbit and you can work out that it's the thing that the star is orbiting is around 11 times the mass of the Sun. And the star orbits that at something like the distance that Mars is from our Sun. So it's an interesting scenario. And I guess the first thing that you would think of is that it's a black hole, because 11 solar masses is kind of in the regime that black holes fit. It would be a quiescent black hole, and that's to say one that is not gobbling up its the gas and dust in its surroundings and causing that to form an accretion disk, which emits light and X-rays and things of that sort. So it's a black hole that would not be revealed by anything other than something going around it. But there is a problem with that, and it's because a Sunlike Star, which probably would be typically about the same age as our Sun, 4.5 billion years, would, in order to have survived that long, would be unlikely to have been in the vicinity either of the black hole or of its predecessor. So the thinking is that this black hole would have come from a massive star that collapsed at the end of its life, formed a supernova, which in itself might get rid of the Sunlike Star, but that then continued to exist as a black hole. And the problem is, it seems that you need to really tinker around with the parameters to make this possibility work. And so the authors of this work have suggested that this is so unlikely that maybe there is a different explanation. And what they have suggested is that this is something called a boson star. Now, bosons are the force carriers, like photons. The electromagnetic force is carried by a boson called a photon. And there's something known as the Higgs boson, which we all know about. Other bosons include the strong and weak nuclear forces. There are two other sorts. So a star that's made of these things is an exotic sort of star, but what they're suggesting is that this is a kind of boson that's not already known. In other words, it's not made of photons, because that would be light. It's something else. And the best candidate for what they're hypothesizing is probably something called an axion, which is a candidate for dark matter. So they're suggesting that this is just a clump of dark matter particles, which are not switched on into a star, because they don't do that. But it's massive enough that we've got this, other star going around it. It's rather an interesting paper. I actually had a look at let me see if I can find the paper again. Here we are. It is, their paper is called, come on, where are you? Here you are. It's called
We're going well today.
I know I am. Yeah, we're doing it all on the fly. Sorry to our listeners and viewers. This is the reality of space nuts. The paper is called "A Sunlike Star Orbiting a Boson Star," and let me just read it because it's written in plain English, which actually tells it like it is. The high-precision astrometric mission Gaia recently reported the remarkable discovery of a Sunlike star closely orbiting a dark object. While the plausible explanation for the central dark object is a black hole, the evolutionary mechanism leading to the formation of such a two-body system is highly challenging. That's kind of what I just said, but perhaps more succinctly. Here, we challenge the scenario of a central black hole and show that the observed orbital dynamics can be explained under fairly general assumptions if the central dark object is a stable clump of bosonic particles of spin 0 or spin 1, known as a boson star. Work that one out. We further explain how future astrometric measurements of similar systems will provide an exciting opportunity to probe the fundamental nature of compact objects and test compact alternatives to black holes. In other words, they're throwing the gauntlet out there. They're saying, well, maybe all the objects that we think are black holes aren't, that they're just piles of dark matter particles and not black holes at all.
Wow. Yeah, I mean, I believe that their research is yet to be peer reviewed.
Indeed, that's correct.
Is that right?
So it's
and they're throwing it open for further study, and I think they even say it's unlikely that this actually is a boson star, and they're urging follow-up observations. So they're just basically saying, look, this is what we've found, this is what we think it could be, but it could be something else, and we really need to take a closer look at this.
Exactly so. That's exactly right. So just something that needs further explanation. And the work was done by two researchers, Dr. Pombo and Dr. Saltast, and I'm not sure where they are, but they have Greek names, so maybe that's a clue.
They could be in Melbourne, if that's the case.
Also true. Let's check. Where they're.
Well, Melbourne is the biggest Greek city outside of Greece.
It is. That's correct. Yes, that's absolutely right.
And I have enjoyed Greek food in Melbourne,
Yes.
from a genuine family Greek restaurant. So it was genuine Greek food.
That's excellent.
Damn nice too.
Excellent. It's good to know, because that's kind of sort of what you need to know when you go traveling.
Yes. One thing that's popped into my head about this is, we've talked in the past about how dark matter is probably not well named, and dark energy has even got a worse name because it's not that. Are we walking down that path again by calling this a dark matter star? Because it's not a star.
Yes, that's right. It's a clump, isn't it? It's a dark matter. You could almost call it a dark matter nebula, because nebulae are sort of clouds of gas. Very interesting terminology there. Maybe it's a sort of the equivalent of a dark matter star. So what is it? It's a dark matter lump or something of that sort.
A dark matter blob.
A dark matter blob. That could be it. These two researchers, by the way, are at the Czech Academy of Sciences, so I was wrong there.
Yeah. Oh, well, so was I. Not in Melbourne.
That's right.
Okay, so this is a bit of a new idea and a new concept.
Yeah.
It's certainly a bit of a curveball in the scheme of things. So when from your perspective, as somebody who's been in the industry for so long, what happens now? Where they've thrown this one out there, is someone going to take the bait and maybe come up with an alternative theory, or what?
Yes, very likely. I mean, in this particular case, what you've got is a sample of one, something that doesn't look as though it's going to be a black hole, but is something else. I think what will happen is that people will maybe trawl through the Gaia data with a bit more of a background in looking for this kind of object, and dig up more of these normal stars orbiting dark spaces. It has happened before. You and I have, in fact, spoken about people finding black holes because of the orbits of the objects around them. But it's usually been fairly unequivocal that it's a black hole. And it's not a kind of normal Sunlike Star that's orbiting around it. In fact, I think we talked about the black hole police, I think they were called, these people who tried to debunk the idea of that all these things are black holes. So, yes, there'll be more observations, hopefully more examples dug up, and a lot of thinking by the theoretical astronomers who will try and make it all work in terms of, what the realistic scenarios are.
Yes, very interesting to watch, and hopefully we'll have more on that in the not too distant future. If you want to find out more about it in the meantime, you'll easily find it on the web at the livescience.com website or space.com. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, Fred, before we get stuck into questions for this week, some follow-up. Ross asked us last week about the brightest of all time in terms of an explosion. And I was a bit off track with what I thought he was talking about, but you've got some more information on the boat.
Yes, the boat. So we got confused, as you would do.
Well, I did. You did.
No, I don't know. Two acronyms with different meanings. The boat meaning the brightest of all time, and the boat meaning the biggest of all time. And what we talked about last week was the biggest of all time. Whereas the brightest of all time turns out to be a gamma ray burst, which was detected last year and has copious amounts of energy. It is the brightest of all time. And I think it might have been Russ rather than Ross. I'm not sure, but Russ's question
could have been
was he had heard that there may be sort of insights into new physics coming from what needs to be explained there, and that essentially is confirmed by my reading of the situation, that the amount of energy that's involved, even if you allow for the fact that this gamma ray burst is formed by a burst of energy that's directed towards Earth. And it is highly collimated. That means it's a very parallel beam of radiation that you're seeing. That to form that there is difficulty in accounting for that observation with what we know about physics as it stands. But you can bet your life that somebody will.
Oh, absolutely.
The theoretical astronomers will get their brains around it. Say, oh yeah, we should have expected this, but we didn't.
Yeah. Well, I think when it comes to astronomy, always expect the unexpected.
Indeed, that's exactly right. Especially when you're doing podcasts like this one, because it's always something unexpected that goes wrong.
Absolutely. Yeah. Okay, Russ. So watch this space again, is what we're saying. And Clyde was asking about dark matter black holes. Was he asking whether or not they could exist?
He was, that's right.
Which is interesting considering we just talked about a dark matter blob.
Yes, that's right. So there's a nice segue from that, which we completely failed to make, but never mind. So that was my fault. Clyde asked whether you could have dark matter black holes, and I sort of waffled about this to say, yes, it's possibly true, because the driving force behind a black hole is gravity, and dark matter experiences gravity. But there are issues, and it's all to do with the way that we know black holes are formed, either by an exploding star of one sort or another, or just the direct collapse of a cloud of gas. And it turns out that in order to make the black hole, you have to have interactions between particles, and in particular you have to have things like friction, things like electromagnetic phenomena in order to make that collapse take place. And the dark matter particles, whatever they are, do not have that. They don't have any other interaction. They only interact gravitationally. And so the thinking is that there would be no such thing as a dark matter black hole.
Oh, yeah. Okay.
Which
there you go, Clive.
Surprised me too.
Yes, until someone proves there is one.
Exactly. Yeah, somebody's sure to come along.
Yes. All right. There you go, Clyde. Hopefully that gives you just a fraction more information. But yes, it's a bit of a work in progress. Let's go to our questions, and I just want to say thanks to Rusty, one of our regulars from Donnybrook in Western Australia, for sending me this Scorpio pic. He took a photo of constellation Scorpio the other day and sent it through. It looks rather spectacular. Must have some great sky in Donnybrook.
They must have.
Rusty.
The constellation is Scorpius, not Scorpio.
Scorpius.
Yeah, Scorpio is what the astrologers talk about.
Oh, of course. Sorry about that. Yes, I know how you feel about that. But this is not about Scorpius. This is about white dwarf stars. But he's taking it a bit further, Fred, and he's questioning astronomers all over the world with this one.
Hey, Fred and Andrew, it's Rusty in Donnybrook. And I have a curly one for you regarding white dwarfs. We've recently discovered a couple in the Milky Way that are 9 and 10 billion years old. And they're not the oldest. They have found one in another galaxy 11.5 billion years old. Its mass is around about 0.55 or 55% of the sun's mass. And the sun is expected to lose some mass, and when it becomes a white dwarf in another 5 billion years, be 53% of its current mass. Now, the sun is a 10 billion year life in the main sequence before becoming a white dwarf, and these white dwarfs are around 10 billion years old. That means that the universe must be at least 20 billion years old. Would you care to explain why that wouldn't be the case?
Rusty. Whoa. Stirring the pot, my friend.
That's right. Well, the universe can't be 20 billion years old because everything we know about it says it's 13.8 billion years old, and that's a very self-consistent picture. So there's something wrong with the interpretation there. And my guess is, and I don't really know enough about the evolution of normal stars at of various masses. I should do, actually, because that's one of the fields that I've specialised in. But I will check up on this. But there must be quicker ways of producing a white dwarf than just doing what the sun will do to produce its white dwarf, which Rusty's right. It will be kind of about half a solar mass thereabouts when it's finished blowing off its outer layers. So white dwarfs, I should have explained, are the end product of normal stellar evolution. A star, when it runs out of hydrogen fuel, goes through various what we call old age phenomena, but eventually ends up with the former nucleus of the star, or the core of the star, becoming a white dwarf, which is electron degenerate. It's only the electrons that are stopping it from collapsing further into a neutron star or a black hole. The interesting thing about white dwarfs is that we have an upper limit for their mass beyond which they explode, and that's why we know the brightness of type 1a supernovae, because they're exploding white dwarfs at a mass of 1.4 times the mass of the sun, which they attain by accreting other stuff. That's the higher mass end of white dwarfs. We're talking about the low mass end of white dwarfs. Rusty, I will indeed follow up on your question to find out what the mechanisms are for forming these low mass white dwarfs, and whether we can do it in maybe a couple of billion years rather than 10 billion years.
Yes. I'll put an asterisk next to Rusty, because that's another follow-up we've got to do.
Well, we've got a good track record on follow-ups for the last week.
Yes. For the last 6 years, I doubt. But
well, 2 out of 100 for the last 6 years, but 2 out of 2 for the last week.
Indeed. Thank you, Rusty. So we'll get back to you on that one. Let's go to David now, who's, we've got another focus on Saturn. Saturn's been big news the last couple of weeks.
G'day, Fred, Andrew. David here from Queensland. Just a quick question, may have a quick answer. Listening to the podcast regarding Saturn and the ring rain falling to the planet. previously mentioned, as we know, the planet is the most oblate. Perhaps it is the deposition of material from the ring rain increasing the equator, or is it just a factor of its gravitational spin? Thanks very much. Love the show. See you guys.
See you, David. Thank you. All right, there's a theory.
Yeah, it's a great suggestion, David. But I think, to quote the time-honoured phrase, I think you'll find.
It's so polite, isn't
it? It's when people are being pedantic and that happens all the time. I think you'll find. No, that wasn't really 1741. It was 1745. Anyway, I think you'll find that the mass of the rings, even if you piled the whole of the ring system onto Saturn's equator, it wouldn't make any difference to the oblateness of the planet, because the amount of material in it is very, very small compared with the mass of the planet. So Saturn's oblateness, which is explained just by normal physics, the physics of rotating bodies, is due to Saturn's rapid rotation speed, and the fact that and probably things like its density as well, because you can get things that rotate faster but don't go quite as oblate. It's so oblate. The oblateness is the swelling around the waist. The fact that the globe is slightly flattened. Actually, pretty well all the planets are oblate, the Earth included. It's got a fatter equatorial.
Actually, if you look at the numbers, it's it might surprise me.
Yeah, it's yes, definitely. I can't. It's tens of kilometers, isn't it? Something like that.
Yeah, it is. Yeah, it's quite a bit.
So I think the answer is it's a nice suggestion, but we think that is probably not enough to make any difference to the oblateness of Saturn.
Okay, there you go, David. Simple. You did think it would be an easy answer, quick answer. So, yeah, you got that right.
The question is, did I?
Yes. Question. Well, it's astronomy, so who knows? Who knows?
Yeah.
And finally, we're going to hear from Jeff, who's got a what-if question for us.
Hi, this is Jeff from Los Angeles. I have a question for you guys. If it was possible to go into a black hole and survive that, go beyond the event horizon, and I know it's not possible, but if it was possible, and one were to look back on the universe, what would they see?
Oh, that's a good question. And
you caught me off guard. He's finished. Yes, Jeff. Thank you.
Sorry, Jeff. Sorry, Andrew.
Well, my thinking is nothing, but I don't know. It's putting spaghettification aside, or linguiniization, as some people have decided it should be.
Yeah.
Let's just assume for a moment you remain intact, you go into the black hole and you want to look out. Well, nothing escapes a black hole, so it's hard to answer the question.
But stuff goes into a black hole, so
yes,
photons can go into a black hole. But I think you're right, though. I think it's dark inside a black hole. Within not inside a black hole, but within the event horizon. Because the fact that stuff is definitely crossing that boundary to be gobbled up by the black hole, and photons must as well. What the viewpoint from within the black hole itself is something that I think is dark, and I think it's because the photons themselves are swallowed up by the black hole. Because there's nothing can exceed the speed of light. I'm actually my logic here is a little bit sus because I'm kind of thinking in vague circles. But I might give some more sober thought to this and confirm
another follow-up.
Yeah, I'll follow it up. But my guess is it's dark.
We're going to do a whole show of follow-ups in a few weeks.
Yeah, well, that's right. We could do that. I think inside a black hole's dark. But I'll need to check the physics of that.
unless you take a torch or a flashlight if you're in America.
Switch your flashlight on, and all the photons immediately get sucked into the black hole, as well as a flashlight and you, by the way. Yeah. I
said we weren't going there. You're remaining intact.
Yes, that's right.
But yes, you couldn't use a flashlight or a torch in a black hole because the light would gone.
Not a very coherent answer, Jeff. I apologise for that. But what is this space? Because we're getting really good at following up.
Yes. There's another 2 we've got to do for next week. Good. Could be a whole new segment.
Yeah.
This week on follow up with Fred.
Yeah.
All right. That exhausts this week's questions, but don't forget, if you have questions for us, send them through via our website, spacenutspodcast.com or spacenuts.io, and just click on the AMA link at the top of the page, and you can send us a text or audio question there, or you can click on the link on the right-hand side of the home page. As long as you've got a device with a microphone, you are set. And don't forget to tell us who you are and where you're from. And I will remind social media users, particularly those who use LinkedIn, which I called LinkedIn for many years before someone told me, what are you talking about? LinkedIn? I never put it together, Fred. Honestly, I looked at it over and over and I thought, what is this LinkedIn thing?
I love it.
True story.
I love it, yeah.
It was ages before I finally got it right. LinkedIn. We're on LinkedIn these days. If you would like to follow us on LinkedIn, just do a search for Bytes.com, BITESZ.com. That's our parent organization, Bytes.com. And we need 150 followers. And once we get 150 followers on LinkedIn, we will be able to stream live, which we want to do. We're doing it on as many platforms as possible. So LinkedIn is one we want to add to our repertoire. So that's where we're at with our social media, as well as Facebook and Twitter and Instagram and some others. One others. That's good, isn't it? 1 or 2 others. But yes, LinkedIn, if you're a LinkedIn user, check us out, bytes.com.
So,
Fred, go on, sorry.
Suggestion for our follow-up, the name of our follow-up segment, Space Nuts, the questions they dare not answer.
That could work.
Could work, couldn't it?
It could work very well.
Real thing.
I like it.
Sorry, Andrew, you were about to wrap up and I interrupted you there.
That's okay. Fred, we've reached the end of the show. Thank you so much.
It's a pleasure, always a pleasure, especially when things keep going as they have done for the last 5 minutes.
Yeah. Well, when you've got to reach a certain time frame, you do a radio trick.
Yes.
It's just called, stretching out.
The keeping going I was referring to was the technology, Andrew. You see, it's gone so well you've forgotten.
Oh, yes. Yes. Oh, I just didn't want to dare hex us with another dropout. Yeah, maybe so. All right. Thank you, Fred. We'll catch you next week.
Great.
Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks to Hugh in the studio for reasons I cannot explain, but thanks anyway. And from me, Andrew Dunkley, always a pleasure. Thanks for joining us. We'll catch you on the very next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.